Now, let me just do an example of symmetric and antisymmetric wave functions using qubits, okay? You've seen qubits, so let's imagine that we have two qubits. So qubit number 1 can be in state 0 or state 1. These are the basis states. And qubit number 2 can also be in state 0 or state 1. And the combined wave function of these two qubits we are going to write as something like this. Always in this order. This is known as a tensor product. You can think of tensor product as just product, like an outer product. Right? So, for example, anyway, I'm not going to go too much into that. So now, if you have bosons, if these qubits are bosons, then we can have symmetric wave function only, right? So out of these guys, the only way we can produce symmetric wave functions are this. This is symmetric under the exchange of the two particles. This is symmetric. But we also have another interesting possibility, which is this. Right? So these are the three possibilities if our qubits are bosons, identical bosons, okay? Because these are the wave functions which are symmetric under the exchange, the application of the permutation operator, right? Now, if our particles were fermions, then we cannot have the first two. These are not possible. The only thing that we can have is this thing. Right? Because if this is our wave function, so P12 psi is this thing. Okay, so this is an example. Now, see that the symmetry and the antisymmetry precludes states such as this, or say this. No, not allowed. Okay. Now for fermions, also states such as this is not allowed. So this means that for fermions, two particles cannot be in the same state. And this is also known as the Pauli exclusion principle. Okay.
Sir, does order matter in tensor product?
Yes, it does. Once you fixed it, it does. Order as in the product, right? Not in the sum.
Yes, sir, product.
Yes, it does.
Is it like when you have X and Y, you can tell which one is X and which one is Y based on their position?
What do you mean X and Y?
Like when you have an ordered pair of X and Y, you can tell the second one is always Y and the first one is always X. So in
Yeah.
this case,
Yeah. Except it don't confuse it with Cartesian product.
yeah.
I mean, tensor product is just product. I mean, it's just like, but you're just keeping track of the different objects.